Good afternoon. My name is Rita. I'm a development manager in Microsoft working on SONiC. Today I'm going to talk about SONiC, obviously. I'll give you a full picture, what it is, how it originated from Microsoft, what challenges are being solved, and how it has been evolved. So why do we need SONiC? Microsoft operates a global set of data centers globally across a wide area network. This represents a multi-billion-dollar bet. That means that we are needing to deliver services with high availability and serviceability to our customers. The customers represent their trust on us who host their applications in a shared compute network, as well as internal customers such as Bing, Office 365. So having a network who's always up is something that we care a lot every minute, every day, and we see SONiC as a key part of this to accomplish this critical mission. We disaggregated the network through SONiC. What does that mean is that we are able to choose different platforms by having a set of APIs. Using the APIs in SONiC, it allows us freedom to choose different platforms as well as different software components. Managing a switch is never just a standalone switch. We need to manage many switches in a huge network. And therefore, we need a system which is fully automated and easy to upgrade and easy to deploy. Having a reliable network enables us to have fast technology evolution as well. So that's the goals of SONiC. Let me give a quick overview of what SONiC is. There are four takeaways for you. First, SONiC is an open source network OS running on top of Linux, so that you could use the familiar OS and familiar CLIs on your hardware. Second, we have a switch abstraction interface called SIDE, which allows SONiC to be ASIC agnostic. So that's very important. Third, it has a network stack which are containerized. What that means is that the stacks are isolated, and it allows us to be able to customize and extend it to our scenarios. Fourth, there are rich toolings based on the open sources in the industry, and you could run different types of tools, for example, Ansible, Kubernetes on top of SONiC. So what is SIDE? So traditionally, in a traditional network OS with different types of ASICs, because they have different SDK, that means that you need to have different ways to talk to them. With SIDE, an abstraction interface, the control plane software could talk to all the different types of ASIC in the same way. So SIDE is basically a set of APIs which using the cross operations over extensible entity attribute value data model. Essentially, we define reference data plane behavior over different types of ASICs. So even though different ASICs might have slightly different personality, but we will unify them so that there is a well-determined behavior, which is the same packet processing pipeline. So what that means is that when a packet is entering this logical pipeline, we know exactly how it's being processed and how it's being forwarded out. This way, the network applications engineers can focus on their business needs without worrying what is different among different ASIC. Since the introduction of SIDE in 2015, whoops. We have seen significant feature growth and partner growth around the SI community. So I'll also give a quick overview of the SONiC software high-level architecture. So hardware switch, if we simplify it, has several main hardware components, namely, for example, the fan, power, LED, transceivers, and of course the switching ASIC. We leverage Linux to manage the platform components. We work with the platform partners to integrate the platform drivers with SONiC. SI APIs are supported by ASIC vendors. The SI API internally would use the ASIC SDK to program the ASIC. SONiC runs on top of Linux, a lot of them in the Linux Unix user space. And here in the middle layer are the key infrastructure components for SONiC. There's a switch service state subsystem. Within it, there's an orchestration agent, OR agent. It interfaces with many network applications, BGP being part of it, and then it pushes the information southbound. The southbound interface is essentially an ASIC DB implemented as a form of Redis database. Then on the right side, there's a SAND subsystem, which will receive the information and then use SI APIs to program the switching ASIC. There's also libraries implemented in C++ and Python, which are wrappers on top of the Redis database, so that users could use those libraries to interact with the Redis database, if they prefer. So the subsystems in SONiC don't send messages to each other directly. The messaging system is built upon the PubSub model with the Redis database, and with this, we are able to reduce our amount of messages that are exchanged directly, that are otherwise exchanged directly between subsystems, and we could avoid race conditions that could easily happen in routers and switches. Another key foundation of SONiC that I must talk about is containers. There are many benefits of containers which are well established in terms of software engineering and deployment. It gives clear, clean isolation software boundary, software configuration settings, and packaging that are required are packaged in containers, and then it can give us, and then you could easily deploy it by orchestration systems. It's also transactional. If you are running one version of container, you have a set of desired state, and you can move it from this desired state to another set of desired state fairly easily through, again, the orchestration system. And it's universal. So we're really good at running software on servers. If we are able to use the same level of excellence and discipline on our switches, we'll be able to provide a very available network to our customers. And again, that is the job number one for a cloud data center. So if we put containerization into SONiC, what does that mean? We can upgrade the software. We can upgrade a feature by upgrading a container. So that's the serviceability. And we could also add new feature by adding container. So we can add one container into an existing set, or we could replace one container with another container fairly seamlessly. And again, in our open source community, we have developers with different development environment. So with containers, we can take software that are developed in different environments, and I'll talk more about that. And then we can deploy it across our switches, cross platforms. So this is the example. For example, routing stack. There are many routing stacks out there, and frankly, you probably cannot get one routing stack that fits all the different users' preferences. So with container, we're able to support different types of routing stack without forcing the same development environment. For example, one could be developed with Red Hat, SONiC is developed with Debian, and then perhaps some are developed with BSD, etc. Another thing is we could also take a container without having the source code. So with container, we can choose which container that fits our, which stack that fits our needs on an individual basis without forcing the commonality of development environment or even the base image. Another example is the monitoring system. Traditionally, you might have SNMP running in your network, right? So we have SNMP as a Docker in SONiC. Over time, you might be working on a telemetry solution in the network. So you could have both simultaneously running in SONiC. And then after, if you have fully migrated the system into telemetry, you could take out the SNMP Docker and just have the telemetry without affecting the rest of the stack in the SONiC. SONiC is designed for both network engineers and software engineers. If you are familiar with the router-style CLIs, operating SONiC is just like operating switches that you're used to. It is also a software platform. Underneath, there is a Redis database associated with the switch state service that I just talked about. You could use a lot of the standard Docker commands to interact with the Dockers of the SONiC. You could log into one of the Docker, or you could list all the Dockers that are available. Here I share some screenshots. For example, the database container hosts the Redis database. The BGP Docker hosts the routing stack. Then you could log into the BGP Docker to see the BGP status, or to see what is the BGP configuration. If you like, you could still use the traditional router CLI show IP BGP, for example. And you could also log into the database Docker to see what are how the routes are actually stored inside the database. Many of the CLIs in SONiC are implemented by network engineers who work with SONiC in a day-to-day basis. They can have direct influence what and when CLIs are available to them to meet their needs. So if you are interested, here's a one-pager how to build a SONiC image. The preparation is that you need a server or a VM with at least 1 terabyte of hard disk running Ubuntu Linux 16.04 or beyond. And then you would want to install a Python installer and a Ginger template for the Python related aspect. And then you can go to the SONiC GitHub to clone the SONiC Git repos. Then you would do some make commands to configure the ASIC platform. We organize the images based on ASIC vendor. Then after you start to do let's say make all, then each module will compile their source code and generate the Debian packages. And then we will further compile into Docker images and then bundle into a single image. You could go to our wiki to see more information. So having an image is just one, right? How do we upgrade? SONiC supports a warm boot feature. What is warm boot? Essentially, it is to be able to do a reboot or upgrade without downtime. The SLA, it's a data plane disruption, is less than a second, but actually many times we're able to achieve without any downtime for the data traffic. With warm reboot, we will reboot Linux OS and we'll reboot the SONiC stack. And the control plane will have a disruption of less than 90 seconds, meaning it will come back within 90 seconds. So that we avoid lag goes down, and also BGP won't go down. And then, and also we will use the BGP graceful restart so that the routing topology will not be impacted, and the stack is able to learn the routes quickly when it comes back. So when the stack comes back, then we will compute the differences between the actual ASIC state and the desired state, and then through the reconciliation, then we can achieve no zero downtime or less than a second data plane downtime across image reboots. So that having a warm reboot capability is very helpful for and important for providing a high availability network to our customers. So able to image and able to upgrade an image is just one of the challenge, right? And I want to walk through a typical data center network topology. So Microsoft has been doing this for many, many years. Down at the bottom, we have a lot of servers, and then the servers are connected to what we call a T0 or rack level switches. The rack level switches are connected to tier 1 switches, or what we call leaf level switches. And then the leaf level switches will be connected to the tier 2 spine switches through redundant links. The tier 2 spine switches will have meshed redundant links connected to other data centers via the regional spine or tier 3 regional spine switches. SONiC is deployed in tier 0 and tier 1 switches in the network. So the network is large, and debugging a data center network is a daunting task. And I'll share an excerpt of a previous presentation from Microsoft as well. So data centers are large and complex. Easily we could have hundreds and thousands of low-cost devices, but running complicated software stack. And then in a daily basis, we could have complex or some packet drops or various types of issues, right? Like packet drop, latency, low throughput in different parts of the network. So existing tools are often insufficient. The common tools are checking counters, ping, traceroute, etc. And I'll walk through why. We could have applications on the client side send requests to servers on the right side, and sometimes they get timeout. And then the application will retry, right? And then the retry may be successful. And then we'll wonder why. Then the operators will then try to troubleshoot what is the intermittent timeout happen. And then we check the switch counters. And very common, there are no significant drops. And then they might try using traceroute, and then even after hours, it's actually still not possible to pinpoint where exactly that transient situation happened. And also traceroute is not able to trace every single path and every single links. It cannot trace beyond links beyond the load balancer. Another example is latency spikes. When there's a latency spike happened, then again, the network engineers or operators try to troubleshoot. The existing queue size watermarks of a switch are often too coarse-grained. It cannot correlate to specific affected flow. Again, the common tools like ping and traceroute cannot measure the per hop delay. So we have a solution called Everflow. Everflow was a joint effort from Microsoft and Princeton University and UC Santa Barbara. And it's also supported in SONiC. We program a set of match and mirror rules into the SONiC switches. The switches will sample traces of traffic into a set of collectors. Then the set of collectors will filter and aggregate those traces into a distributed storage. We built an Everflow controller with a number of applications. The controller will expose the query API, queries via a set of APIs to the applications. One of the analysis applications is packet drop debugger. When there is any packet drop happen anywhere in the network, it can quickly identify which might be the suspected switch. And then with the guided prober, then we can further confirm which exact switch is dropping packet and which specific interface. And also using the Everflow solution for latency spikes, using the solution, it can also identify or confirm where exactly the latency occurs. So this is one example of how we integrate SONiC into our data centers to solve the challenges. So over the years, we've added a number of features into SONiC. The first year, 2016, when SONiC was first released, it supports basically 2.3 functionality with a solid Docker container architecture and a Raiders database. In the second year, we added more advanced features such as RDMA support, IPv6, Docker management via Swarm. And then the third year, we added streaming telemetry, beef up the config database, and added the warm reboot feature, which I just talked about. There's also virtualization features. Last year, we spent a lot of efforts to add an advanced management framework with the contribution from the community. We improved the development and test experiences and continue to add more rich features such as NET. In terms of ASIC and platform, in the first year, SONiC is supported in 5 platforms with a few ASICs. After 4 years of contribution and efforts by the community members, now SONiC is supported in 92 platforms and as well as most advanced chipset. It's truly a collaborative effort by the SONiC community. We appreciate the members who stay with us, such as Broadcom, Dell, Mellanox, and we continue to add members in the past over the years. Last year, 13 organizations joined, including Juniper, Baidu, a few research institutions. SONiC is an open community, and we invite your participation. Go to our website. There are user manual, quick start guide, and then you can come to the community to participate in design reviews. Try out the software or hardware, and then you could test and deploy, and you might find bugs, and you could also report the issues. By working with the community and the partner ecosystem, we're looking to rationalize the networking today and into the future with SONiC. Thank you. Any suggestion or questions?
Thank you for the presentation. Question is, half of hardware vendors you presented support in-band telemetry in different forms. IFA on Broadcom, what just happened on Mellanox. How do you plan to integrate it and enable people to consume this information? In-band telemetry.
I'm sorry, can you repeat the question? How do...
In-band telemetry on hardware.
How do we invent telemetry? Is that the question?
No, hardware vendors that support SONiC have their own implementations of in-band telemetry. So IFA on Broadcom, what just happened on Mellanox, Int on PE on Barefoot. There is some code being pushed into SONiC as of today, actually, but has this functionality, but it's unclear how it's going to be exposed and how people can use it.
Sure. So actually, in terms of telemetry, there is actually this design document for telemetry in SONiC, right? And then typically, a feature is implemented has two parts. One is the SONiC application side, and then there is the side part. So, so we would work with the vendors to support the side APIs to expose the telemetry capability. Yeah, does that address your question?
It's a very generic answer.
Yeah. So I mean, telemetry has a lot, right? So, but for example, it's important to define the side APIs for telemetry. What are the information that needs to be exposed or can be exposed? And then it depends on the ASIC capability as well. But then the side API needs to be generic enough such that it can cover perhaps a unified or a union of all the capabilities. Yeah.
Okay, thank you.
Yeah. Thank you.